Hi folks, welcome to your IGOR3 video instructions. In this activity, we are going to be creating a phase diagram. So you can see this nice, lovely phase diagram of water. I created using the instructions I'm going to give you. So you're going to put all this lovely detail, all these equations. So these are actually like the real, phase boundaries. For this assignment, you're going to pick any molecule or atom that you want. I recommend doing something simple where there's a lot of data available. So I did water. You can do water too if you want, or if you want to do something, like carbon dioxide or anything else, right, that you can find data. That's totally cool. And you should primarily focus on the first order phase transitions. So like the solid, liquid, vapor phase transitions, okay? So let's see here. So this is my final product that you can see that I've got. So I'm going to give you enough instruction to put together the phase boundaries and a few of these details. But from there, you're going to need to do the rest of it on your own. Okay. So I've got this IGOR code cheat that we're going to use. And so here I'm giving you the codes. Okay. So let's zoom in on that a little bit. And before I get straight into all of these codes, I want to just spend a minute showing you how you can find data for your molecule. So there's a number of ways, but one of my favorites is through this NIST chemistry webbook. So you can access, let me back up all the way. So let's see here. So you can find this. So here's the website. You can see, I just Googled NIST chemistry webbook and right here it comes up. Okay. So there's a number of ways that you can search for things. I'm just going to search by name. And let's just look at data for carbon dioxide, for example, okay? Search. So we get all kinds of great information here. And what, to point out here, the thing that we really want is the phase change data, right? So let's take a look at that. So sweet, look at this. We get the triple points, and we even get references with those triple points and even uncertainty in them. Right there's the pressure triple point. Look, here's the critical temperatures, and there's a whole mess of them that we could choose from depending on our favorite reference. Critical pressures, critical volumes, critical densities, even the delta H of vaporization, which you're going to need, as well as the delta H of sublimation. Okay, so there's all kinds of data on this NIST site. And of course, if you can't find other data that you need, then go to the web. So for example, another set of data you're going to need are densities, so that you can calculate the volume. So since I did water, here is a data page I found, or a graph of density for water. And you can see that this gives me some really precise detail. So I got my values by reading them directly off the graph. And you can see when you make a nice graph with all of these dotted lines, it makes it really easy for your audience to read information off the graph. So first thing you want to do is pick the molecule that you want and find all of this data. Okay. So now, before I walk you through my IGOR codes, I'm also going to show you, I'll highlight one of these lines here. So you'll notice here that I needed, so first I'm going to show you is the solid liquid boundary. So you need to have the enthalpy of fusion. So you need to find that, and you're going to need to find the delta V of fusion, the change in volume. You're likely going to have to calculate that, okay? So I'll remind you to calculate, to calculate delta V of fusion, for example, we're going to need to have the molar volume of the liquid minus the molar volume of the solid. And I can get that by using the density, okay? So as you can see, the way I plugged in my IGOR code, look, I've already put in, I'm gonna have IGOR calculate it for me, right? So that's why I said, this number minus this number times 0.001. I'll tell you what that 0.001 is in a minute. But as a quick example, here is how I calculate this change in volume. So because this is for fusion, I want volumes that are at or near where that phase transition takes place at 0 degrees Celsius. Okay, so here you can see this is definitely evidence of a first order phase transition from our Ehrenfest classification of phases, right? There's a giant change in volume at 0 degrees. So here is the density of the liquid, right? Because it's going above 100. And, you know, if I zoom in really quick, or this graph zoomed in for me. So let's say, you know, the density of water at 0 degrees. So this is 999.8. This tick would make it 999.85. So I'm going to call it 999.84 kilograms per meter cubed. Very quickly, I recognize that's the same as 0.9984 grams per milliliter. Hopefully, your chemistry major, you can just do it like that, okay? Let's see, do I have a calculator in front of me? So what I'm gonna do is now write this as in 1 milliliter, I have 0.99984 grams of H2O. And my goal for this molar volume is to get this in mole per cubic meter. Okay, mole, or wait, hold on, backwards. Cubic meter per mole, right? Because it's a volume. So the volume unit has to be on top. Cubic meter per mole for molar volume. Okay, so now what I can do is say water is 15.9999 for oxygen plus 2 times 1.008. So I'm going to get some really, a lot of digits here, okay? So 18.015 grams in 1 mole. And I know that there's 1,000 milliliters in 1 liter. And I'm just going to leave my calculation. Well, actually, yeah, let's go ahead and keep doing it. Okay. So then I also know, because I got to make this in cubic meters, okay, there is 1,000 liters in 1 cubic meter. Let's double check that just to make sure. Let's see, liters to cubic meters. Yes, 1/1000th. Okay, great. Yes, 1 liter is 1/1000th. Okay, so 1/1000. Perfect. So here we go. Okay, so then when I do this calculation, let's see, I get 18.015 divided by 0.99984 divided by 1,000. Okay, and I'm just going to stop here for a minute. So I get like something like 0.0180 something, blah, 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 blah. So if you look at my code here, look how I wrote that, right? 0.0180, et cetera, et cetera, et cetera. So this right here that I put in my code is technically the liter per mole, okay? So like, you know, 0.0, I'm just gonna use a couple sig figs, 0.0180 liter per mole. And so then what I did, so that's my molar volume of the liquid. So now the second number right here, that's my molar volume of the solid, which I got from reading off this point on this graph. And here I followed it along, and so you can see, so this is 910, this is 920, so this tick mark is 915. And so I would say that that's somewhere in between. So I'm going to estimate the ice as 917. And that's all that I can get from this graph. So I get 3 sig figs in this density right here. So I'm kind of cheating the sig fig rules a little bit, but I just want to show you where I'm getting these numbers, okay? And I'm not going to convert this, but this goes on to give me the molar volume of the solid, right? This was my molar volume of the liquid. And then what I did in my code, and certainly you could copy it the way that I've done it here, or you could just directly do the volume. So when I enter this in IGOR, I'm going to say this minus this, and then times that additional 0.001, the 1 over 1,000, to get it into cubic meter per mole. Okay? And so now what I then collected my triple points, and this is going to give me my equation. So this is the same code as the equation, and then this displays the line. So let's go ahead and travel over to a new desktop. Oh, hello, Eureka Slow. And we're going to open up an IGOR and get this thing going. So definitely take your time to collect all the data you need before launching into this. Some of you will say, oh, Harmon got all the data for water. Do something different than water, right? Go find some new data, okay? So now I'm gonna rearrange my IGOR window the way that I like it. So I was like kind of expanding this command prompt right here, and I've got my data browser. Great. So now I'm just gonna start entering in these codes, okay? So we're gonna say make n equals 10,000. So we're gonna have 10,000 data points. And I'm gonna call this wave the pressure of the solid liquid boundary, okay? So now I just made a wave with 10,000 data points, and the name of that wave is P underscore solid liquid, all right? You don't have to be exactly like I do, but you can do that if you like. So now those 10,000 data points, I'm gonna set it over a temperature scale. And so now here I'm doing the solid liquid boundary, and I just randomly chose 223.17. Sorry, I did not randomly choose these. I specifically chose that I'm gonna make that X scale 223.17 to 273.17, because what I'm plotting is the solid liquid boundary. That's not going to extend past the triple point, right? I'm not going to have a solid past the triple point. And so you might be saying, well, the triple point is 273.16. So I found, because of this natural log relationship, giving it one extra decimal past ensured that my triple point crossed all of the boundaries. So my recommendation to you is to, when you're finding your molecule, just go maybe 1/100th past where you know it exists as a phase, and that's going to ensure all those lines actually cross and look nice. So what I'm doing is now I'm saying those 10,000 data points are going to be spread out between 223.17 and 273.17. So I'm going to have some very precise data, right? I'm going to have data points with a very small delta t. Okay. So now we're saying set scale 223.17 to 273.17 of that new wave that I just created. And now, before I enter my equation, I need to define my variables. Okay, so you got to do this first. Do this in order. That's why I'm giving you this cheat sheet. Okay, so variable DH fusion. I looked up this for water. This is 6010 joules per mole. Got to be in joules, not kilojoules. You know, I only have 1, 2, 3, 4 sig figs on there. Maybe we, find more sig figs if you can. Okay, so now I'm going to say variable dv fusion, and I'm going to have IGOR just calculate this stuff for me. But certainly if you calculated just the change in volume directly in meters cubed per mole, you could enter that in, and then times 0.001. So entering it in like that, IGOR does the calculation. Okay. So now I want to explain here why I'm using the triple points. Okay. So if you recall, when I derived this equation in the lecture, this P2 is connected to T2, and this P1 is connected to T1. So that means to use this equation, I have to supply values for P1 and T1 specifically. And I have to do that for 1 and 1 because the equation is designed to give me P2. So this equation is really saying like P2 is a function of T2, okay? And furthermore, because this is the solid-liquid boundary, I want to use values that I expect to exist on that solid-liquid boundary. And so I know that the triple points will exist on that solid-liquid boundary, okay? So now my triple point that I'm going to define here, variable PTRP, so that's the triple point. So this 611.657, that's in units of Pascal, okay? Because if you think about this, right, if we're doing Kelvin and cubic meters and joules and moles, our units of pressure has to be in Pascal, okay? So make sure that you are getting pascals for pressure. So there's my triple point. Now let's define my temperature triple point, TTRP, and that's 273.16 Kelvin, right? Okay, and then now finally I can define this equation. So so my wave name is P underscore solid liquid. I did that for my own cognition so I can find it later, right? You guys know the IGOR files become a mess. And I'm gonna say P solid liquid equals. And so now all of the stuff that I got is copying down this equation, but instead of saying P1 right here, I'm gonna say P triple, okay? So P triple point plus, and now the ratio of the enthalpy of fusion to the enthalpy of fusion times, and then now the natural log, and then check this out. Instead of saying T2, I'm just gonna say X, because that is my independent variable in this phase diagram, okay? So X divided by T, TRP, parenthesis, and then I think I can hit enter, cross your fingers, woohoo, okay. Actually, here's where I need to cross my fingers. Display P underscore solid underscore liquid. Beautiful, I got a graph, okay. Now what I wanna point out here is I talked about in the lecture how with stuff like water's the only one, it has a negative slope for the solid liquid boundary. For anything that you pick, because you're not gonna do water, right, you're gonna see a positive slope. I also want to point out this is a ginormous scale that's going on here. So we're gonna be using log scales. So I'm going to right click on here. I'm going to arrange it so I can see it, okay? And just very quickly, this is not the graph that I'm going to format because we got to get all three of these boundaries on here. But I'm going to push log and look how that changes, right? And also I want to point out when I go to my axis range, so it's starting at that triple point because that was my first value. What I recommend doing is, so just saying 1. Because if you say 0, it doesn't like this at all because you can't take the log of 0, right? So I'm going to start this at 1, and I can also see this is 7.7 times 10 to the 8. I'm just going to say 1e to the positive 9 to make it a nice even value. And look how nice this looks on the log scale, right? That's pretty cool. And if I put my cursor on there, we can see how well it reproduces the triple point. So there we go, at 273.16, the pressure is 611.66 Pascal, and that's what it should be. And you can see, because this is a log scale, right, it shoots up within the first couple data points, but then it takes it forever to scan through the other data points because I've made 10,000 of these data points. Okay, let's move on to the other boundaries. Okay, so let's see here. So I'm going to switch to the page. So now I've got the liquid vapor boundary, and we're going to enter two things here for the liquid vapor boundary, and I'll tell you why. And I'm just going to do this kind of quickly because I gave you explanation of what I did last time. So 10,000 data points. This is now liquid vapor, and I'm going to call this P underscore liquid vapor 1. We're going to do this twice, and you'll see why. Okay, And then now I'm going to say set scale. Okay, so now because this is my liquid vapor line, I'm going to say 273.16, and I'm going to take this all the way just a little bit past the critical temperature. So I'm going from 273.16 all the way to 647.10 Kelvin, just a little bit past the critical point. Okay, P underscore solid underscore liquid underscore 1, so it's got the same thing. I looked up, oops. See, Igor told me that it wasn't happy, right? Because I didn't name it consistently with what I did above. So liquid vapor underscore 1. Okay, great, it took it. So now I'm ready for all my variables. So variable DH vape equals 40,680 joules per mole. I'm going to define R, and Igor doesn't like when you use just R. It's something, I don't know why, it doesn't like it. So I say R underscore equals 8.314. And now I can define my vapor boundary. And notice here I've got the equation right here. It's the Clausius-Clapeyron equation. And just like before, I've got my P1 and my T1. And this is why we're going to do this twice. We're going to try it doing once using the triple point at 273 and 611 Pascal. And then we're going to try it again using the boiling point at 373 and 101,325 Pascal. And we're going to see that there's differences. There's some errors that manifest, okay? So we're going to say, oh, you know what I just noticed here in my Mathematica code? This is wrong, okay? Look, P underscore liquid vapor, that should be P underscore liquid vapor 1. I'll fix this document for you all. Okay, so PTRP, so I'm going to first use the triple point. PTRP times the exponential of negative parenthesis DH vape, the delta H of vaporization, divided by R, and then times double parenthesis, and then again, X is really a placeholder for T2, which is my independent variable, and then minus 1 divided by TTRP, my triple point. I think all my parentheses are closed up. Let's see. No, it wasn't happy. So, okay, I have too many parentheses or not enough parentheses. Maybe not enough parentheses. There we go. Okay, so I got to fix this thing. I'm going to highlight this so I know to fix it. Okay, great. Bueno. So now I'm going to display it. Display P underscore liquid underscore vapor underscore 1. And that looks like the Clausius-Clapeyron relationship. Perfect, an exponential rise. So let's do this a second time. And now what I'm going to do, check it out. I can say, so I'm going to copy all of this code. This is why I like expanding this thing so you can move this thing up and down. And I'm just going to now replace some stuff. I'm going to replace the 1 with the 2. My temperature range is going to be the same. Replace the 1 with the 2. I don't need to redefine my delta H of vape and R. They're already defined, so I got rid of those. And now I'm going to say P underscore liquid underscore vapor 2 equals, oh wait, sorry, I got ahead of myself. Okay, so now I'm going to kill that. No save. So how far did I get with this? Okay, so I defined it. I got the set scale. Okay, so now I'm just going to redefine the equation. So I'm going to say variable. Now I'm going to use, instead of using the triple point, I'm going to use the boiling point or the vaporization point. So 373.15. Okay, I'm going to say now variable P vape. So remember, 101,325 is exactly 1 atmosphere, and so water boils at 373.15 Kelvin at exactly 1 atmosphere, right? So that's where that comes from. Now I should be able to redefine this second equation, but instead of saying the triple point, I'm gonna say the vaporization point. So I gotta change it to P vape and T vape, and it took it great. And then now what I'm gonna do, okay, so I could say display, but I'm gonna show you how I can actually start building this up. On this solid liquid boundary, I'm gonna say Windows, or excuse me, graph, append to traces to graph, and I'm gonna select both P1. Look, I can do, I can hold the shift or the control button and select both of these versus calculated and say do it. And look, there's some differences. Okay, so let's make one of these a different color. Okay, so then I'm gonna make, so now let's see, the one that is red is number 2, and so that's the one that I used the boiling point for. Okay, and so I'm gonna highlight a few areas here. So in IGOR, I can draw a box like that, and I can right click in the box and say expand. And so you notice that the red one, so remember the red one is the one that I used the boiling point for, and the black curve is the one that I used the triple point for. And so now you'll notice here, so if you follow here, so P liquid 1, so it's saying at 273.16, the pressure is 611 Pascal, and that's correct. But look, the red curve, the curve that I used the boiling information, it's saying the triple point at 273.16 is 834 Pascal. And we know that's not correct. And so now I can say Command Z, and I get back my scale, so you can do Control Z for a PC user. And so now let's go up to near the boiling point, and let's see how well this thing does. Okay, give me the boiling point, please. There we go. Okay, so 373. We're gonna scale it all the way down here. I got a lot of data points to go through, so there we go. Okay, let's see here, let's see here. So I think you can probably see where this is headed. We're gonna see now which curve reproduces the boiling point. Okay, so I've got my cursor B on the boiling point, and let's get my cursor A on the boiling point. Okay, wonderful. So now you can see that, and so if I expand on this again here, so the red curve is number 2 here, and it's saying at 373.15, so 100 degrees, the pressure is exactly 1 atmosphere, which it should be. But this curve is now saying at 100 degrees, it's less than atmospheric pressure. So what do I need to do to get that thing up to atmospheric pressure? And so that'll tell us like how far off my temperature is. So I can maybe move it to about right there. So let's see here. So I want 101.3, so there it is. So man, that's off by 9 degrees. That's some serious error. And that is to be expected in phase diagrams, because if you think about it, we didn't put a temperature dependence on the enthalpy of vaporization when we derived the Clausius-Clapeyron equation. So there's gonna be some large errors in phase diagrams because of this. This is to be expected. So when you're putting your phase diagram, I'll kind of give you freedom as to which data point you want to reproduce. So you have your choice here of which one. You could even do something really creative where you include both. So watch this. I can, hopefully this just works on the fly when I do this. I'm gonna make, do the whole fill to next trick. So let's see, what I wanna do is go to graph and let's see, reorder traces. And I want to make it so that the red one is on top so it fills down. And so I'm going to move that up. So it's the top, and I'm going to make the number 1 right underneath. And hopefully this works. Okay, so let's see. We'll say fill to next. We'll give it like a shaded area. Sure, why not? Yeah, that's actually not so bad. So you could even do something like that for your phase diagram if you wanted to. If you wanted to highlight that there's some errors in these phase diagram calculations, okay? And so finally, the last one we're going to do now is the solid vapor boundary. And it's almost identical to the liquid vapor boundary, except for recall, we use the delta H of sublimation. So let's enter that in really quick. Make n equal 10,000 data points. And then now I'm going to say P underscore solid underscore vapor. And we're just going to do it one time. Set scale. And then my scale, again, because now we're talking about sublimation, this has to exist between, you know, like, I'm going to say 223.16 and 273.16. And you can see this is why I also said 0.17 for the other line, because now when they intersect, there's going to be an overlapped area right there, okay? And then P underscore solid underscore vapor. Okay, great. So now I have to define the variable dH sublimation. I looked up that for water. That's 51,100 joules. Okay, great. And then now I can define this equation, P solid vapor. It's the same equation as before, but now you notice here, for P1 and T1, I'm going to use the triple point because the solid vapor boundary exists fairly close to that triple point. So I'm going to have some really accurate, it's going to be more accurate if I use the triple point for this particular curve. Okay, so negative parenthesis dH sub divided by R underscore parentheses, okay, times. And then again, I'm using X as my independent variable, place for T. 1 divided by T, TRP. Okay, and then make sure all these parentheses are closed. Wonderful. And instead of saying display, I'm going to just append it to this graph directly. So graph, append traces to graph. And now I'm going to pick my solid vapor boundary versus calculated. Do it. Look at that. That's awesome. Okay, there it is. Very cool. Okay. So now there's a few things I'm going to highlight. Let me bring my super fancy phase diagram over here. Okay, so this is my completed example. It's got all those curves in there, but you can see I added legends. I added grid lines. I added these annotations to highlight the freezing point and the triple point and the critical point, okay? I want you to do all that. I want you to highlight all of these things. And I'm going to show you a cool trick how you can get these lines right here, which, and by the way, so this, my blue line right here, this is just a really thick line that I made in place of this shaded area. So that's how I chose to do it. And you can see once you're on this crazy big scale, you don't really see that error, right? If I was dragging my line across, so I know 10 to the 5th pascals is atmospheric pressure. And if I scan down, I mean, you can see like, it's not bad. There's 360, there's 370. It's okay. You know what I mean? If I'm using my eyeballs instead of the cursor, all right? But the important thing is I've got the triple point. Everything is intersecting at the triple point. So let me show you how you can get some of these really slick lines. Let's get this thing out of here, okay? So I'm going to go and say window, new table, and just do it. I'm just going to get a blank table. And what I want to do is make a series of vertical lines that go across. And I'm also going to like square off my scale here. I think it's nice if you make a nice even scale. So instead of this 223.16 and these crazy numbers, I'm just going to say like 220 and 650, you know, that evens it off really nicely. And then on my left scale, that's why I'm just going from 1 to 1 times 10 to the positive 9. You know what I mean? Just nice, even numbers. And it's okay, like, if my curve doesn't bottom out there exactly, okay? Because we know that it should. And we're not going to do any data fitting on this, so it's okay. And I'm going to take my mirror standoffs. I'm going to put my mirrors on. Let's see here. Left. Mirror on. And I'm also on this log scale. The ticks can look pretty good, but they usually don't show up. Yeah, those log scale ticks usually don't show up unless the graph starts to get pretty big. Okay, so now let me show you how you can make a really cool vertical line. Okay, so first I'm going to give it a data point of the entire range of my graph. So I'm going to say from 220 to 650, because that's what I made my range. And now I'm going to say 101, 325, and 101, 325. So wave 0 versus wave 1 is just going to give me a straight line at atmospheric pressure. So I'm going to say graph, append traces to graph, and I'm going to make wave 0 is my x and wave 1 is my y, right? Because the y scale is pressure in Pascal, and the x scale is temperature in Kelvin. Okay, so do it. Awesome. There's a line right there. I can also make a line for the triple point. So I'm going to do the same thing. I'm going to say from 220 to... Actually, I don't even need to do that because I can just keep reusing wave 0. So instead of saying 220 and 650 again, I'm going to reuse the triple point, which I think was, let me find it. Oh yeah, 611.657 Pascal. So I'm going to say 611.657, 611.657, and then now I'm going to append that line. So now I can still use wave 0 as the x, right? I don't have to define it again. And now I can use wave 2, do it. Awesome, I got that reference line right there. And now let's make a reference line for the critical point, okay? Which is, let's see here, I know it's in here somewhere, the critical pressure. Oh, I didn't have to use it for this exercise. Okay, so I'm going to cheat and grab it off of my phase diagram. Where'd it go? I think so. Okay, hopefully, so off the top of my head, oh, wait a second. Duh, I've got my NIST data. Water. Okay, phase change data. Critical pressure. Okay, so let's use just roughly 220. I'm just going to use roughly 220.5 bar. And there's a really cool trick. 1 bar is 101.325 Pascal. Okay. So it's 220. Let's say 220. Yeah, I'm just going to use like some middle value just for the point of this. 220.5. So it's going to be 220.5 times 1e to the 5th. Okay, so that's 2205.0000. Okay. 2205.0000. Let's make sure if I did this correctly. Yeah, that's right. It's 22 megapascal. So 2.2 times 10 to the 7 Pascal is 22 megapascal. So now, once again, I'll put that reference line, append traces to graph. I can still reuse wave 0 as my x, and now wave 3, do it. Awesome, look. And you can see, actually, that's kind of to be expected. That's pretty cool. It split the difference between my two curves there. That's actually really cool that it split the difference between my two curves based on whether I used the boiling point or the triple point. Yeah, so you can see it's like, you know, it's right in between there. Okay, great. And now I can say Command Z. Okay, so basically from there, look, I've got all of my reference points And the rest of this is just making this look really nice, adding those graphics, right? Adding those grid lines, adding those text information, right? So let's see here. I lost my file somewhere, wherever the hell it went. Okay, anyways, I'll have it on the, for reference, I'll have that figure. I think I do have it. Oh, duh, here it is. Okay, great. Yeah, so you can see now all of the extra stuff I did, right? Oh, yeah, so I used 22.065 megapascal at 647.10 Kelvin, okay? So you can add all of this lovely stuff on here to tell me what's going on with your graph, okay? And let's see, so for the final product, this is what you're gonna make. You're gonna give me a nice detailed phase diagram. You can make it big. I didn't give any requirements on the size of the figure, but you should make it big, like the size of a page, So maybe right here, something like, 6 by 6 or 7 by 7 would probably be appropriate. You know what I mean? Like a nice big square box. And no descriptions or anything like that. Just the phase diagram is fine. You got to indicate somewhere on here what the material is. So here you can see I've got H2O. Okay. Yeah, so have fun with this. Be creative. Find your favorite molecule. Get all of that data. And like I said, don't hesitate to reach out to me if you have any issues. Okay, folks. Let's have some louder. Okay, I'll see you later.